Alright, we are back. And on the last video, we are solving the example 2.22 from the third edition, this example. And because I wasn't able to find the angles phi n and phi o, the angles of pitch and yaw, I said that on this video, uh, we will solve the example 2.21, I think, from the second edition. Right now, I'm not with the book, so I don't know exactly what is the number of the exercise of the second edition. But the only thing that it changed is the coordinates of the matrix that we will use. But something that I should done um, on this example, solving this example, it was to find the solutions for these angles, but using the cylindrical coordinate system. And I will show you how we can do this, because as you can see, we are using the solutions for the angles, but with the Cartesian coordinate system. As you can see, AY, OY, and right here also I was just being lazy and I used this matrix of the Cartesian coordinate system, and we were doing something like for example solving one example before this one, which is the 2.21. We were doing nx is equivalent to this element of this side of the equation, and to solve this I was just being lazy and I said that, for example, the cosine of alpha is equivalent on the Cartesian coordinate system matrix to nx, and we were taking this element and trying to solve for cosine of alpha. But instead of doing this, remember that I said we got two ways to solve these examples, and the second way is exactly to solve for phi n, phi o, and phi a, but using the solutions for the cylindrical coordinate system. And let's do just a quick review so you can understand better what I'm trying to explain to you. First of all, at the beginning of this topic, in which we are talking about the angles of real pitch and yaw, first of all, to remember that for construct these characteristical matrices, we need to see in which direction these axes of these angles are pointing on this another system. For example, the a-axis of this reference frame of this system is pointing on the same direction as z of this other coordinate system or reference system, reference frame to be more correct. That is a reference frame, and this one is another reference frame. So A is pointing on the same direction as Z, so we got the characteristical matrix of rotation above the Z-axis, and we adapt to this matrix. And right here we substitute the angles with their respective angle. So A is the angle of rotation. Sorry, A is the axis in which we apply the rotation of rho, which is respectively the angle of A. Again, N is pointing on the same direction as X, so we use the characteristical matrix of rotation above the x-axis, and we adapt to this matrix. So the angle of pitch, we apply this angle above the n-axis, and we obtain this characteristical matrix of rotation. All right, so applying both of these rotations, we got this characteristical matrix, RPY. So if we multiply both of these rotations, we got this total matrix. Okay. And all right, we have done a inverse kinematic analysis of this of the rotations of rho, pitch, and yaw, which are done simultaneously, or they can be done in sequence. And when I say successively, because I think it will be more easy if I showed to you if with a example, with a simulation, will be more easy to understand if we saw this occurring in a robot arm. Visually is more easy to understand. So again, I will use the RockSim 1.7 version, and I will try to illustrate this with this robot arm. Okay, so I will click right here, and right now, look how nice it is. If you're a pair, follow the pointer of the mouse. Can you see the pointer of the mouse right here on this tool, on the end effector? If you repair, we are changing the whole system. We are changing the whole body. We are changing the angles of the joints. We are changing the position of the links. But this point right here, it remains the same. It doesn't change at all. And this is the power of a RPY matrix. Look how nice it is. We are changing the whole system, but this point, it remains without any change. And now I will change something just to mess with the system. Okay, again. Can you see? We are changing the angles of the joints. We are changing the position of the links. But this point, it remains without any change. And now before we go on, I will try to illustrate with a draw what is this rotation above this axis that we apply in order to the couple angles, and when I'm apply this transformation above the a-axis with some, let's say, some alpha angle, and it's a inverse transformation we do because we don't want to change um, um, if I'm saying that it doesn't change the orientation, um, sorry, if I'm saying that it doesn't change the position, um, so that is right. And for the orientation is the same. And again, as I said before, if you try to apply um, a rotation above the n or the o-axis, it won't produce the same result because these angles, they are not pointing on the same direction as the z-axis. So this is works because we are applying this this rotation above the a-axis. Okay, so we got this another reference frame, A and O, I think, and we will apply now a rotation right here. Now let's see the simulator again, and now I will click right here to add reference frames on each joint. Okay, so let me see. Well, as you can see, this axis in blue, it's not changing its position and its orientation. Let's see, I will try to turn to the right the end effector with the 2. Okay, but I also wanted to see, let's see from here. Well, as you can see right here, this axis in blue, the position and orientation, it doesn't change. And it's the effect that we got with this technique. Okay, okay. So right here we have multiplied both sides of this equation. The both sides we have multiplied by the inverse of the of this rotation above the a-axis. So is the inverse transformation of rotation above the a-axis with the angle phi a. So I multiply this side, and these terms they got cancelled, and we will obtain this following transformation equation. Okay, and with this transformation equation, this RPY matrix, we said that for a Cartesian plus RPY robot, we assume that we wanted that the final position, the final desired orientation and position, we wanted that to be with these coordinates. Because we wanted to solve the angles of phi A and phi O and phi N for the Cartesian coordinate system, and that is because that's why we assume that this matrix is corresponding to this RPY matrix. Okay, so multiplying these two matrices, we got this matrix, and multiplying these two matrices of this right side of the equation, we got this matrix. And as this is a equation, we can say that for each element on this matrix on this left side, we have a equivalent on this matrix on the right side of the equation. In this way, we have solved it for phi A, phi O, and phi N. We have applied the tangent, this relation, and apply the arctangent. We are able to extract the angles. Okay, and on this video, what we will do is the same process, but using the matrix of the cylindrical coordinate system. So let me find this matrix, the matrix of the cylindrical coordinate system. Right here, we got one. Right here, this one. Exactly. Right here. The cylindrical coordinate matrix. So let me copy. All right. let me see. We will do the semi-process. So now let's see, the final desired orientation is on the cylindrical coordinate system. Alright, that is the final desired position. Alright, on the right side we have already multiplied, and it is equal to this matrix. Alright, and now we have to multiply this left side. Okay, so let's use the octave. So type clear all to clean the octave's memory, CLC to clean the command window. Now we can type pkg load symbolic, and this way we will load the package symbolic. Now we need to pass the parameters. Is first type sims. Now the name of the parameters that we will use on the matrices is phi A, phi O, phi N. Let's see what else. We will use now again alpha and R, and also L. Alpha, R, and L. Now we need to entry with the matrices. So let's construct the matrices. Okay, the first one is cosine of A minus sine of A 0, 0, Sine of A, cosine of A, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, this one is already to use, ready to use. And pasting right here. Okay, now the next one. Cosine, no. Let me see. I'll have to change right here. Okay, cosine of alpha. Cosine of alpha minus sine of alpha. Sine of alpha. Cosine of alpha. 0 or times cosine of alpha, and right here also or times sine of alpha, and 0, 0, 1, and right here is L. 0, 0, 0, 1. Okay, and we will call B. Now we just have to type A times B. Right. Now let me take a print. We print screen. Okay, and I will paste right here. And now we just have to write down the elements. So, and I'm having a problem with this signal. I don't know exactly because of this -1 superscript of this inverse transformation. I could just see how I can do on the correct way on the matrix, but I'm just lazy about this. And let's see what we will obtain as result. Minus sine of alpha. We change the color. And because also I wanted to entry with other topic, because this is taking too long. Sine of VA plus cosine of alpha cosine of VA sine of alpha cosine of VA plus sine of VA times cosine of alpha 0 and 0. And the second column minus sine of alpha times cosine VA minus sine of VA cosine of alpha minus sine of alpha times sine of VA plus cosine of alpha times cosine of VA. 0 and 0, and right here 0 0 1 0, and the fourth and last column minus r sine of alpha times sine of VA plus r let's see, minus r sine of alpha times sine of VA plus r cosine of alpha times cosine of VA, and r sine of alpha times cosine of VA plus r sine of VA times cosine of alpha, and L and 1. Okay. A huge matrix we got. Just to write this equation. Alright. And each element of this matrix of the left side, for each element, we got a correspondent element on this matrix on the right side. And this way, we can construct equations. Okay, so the first equation that we will write is this one, with this correspondent element on this other side 0. So will be this one with this one, which is equal 0. And let's see right now. As I said, I'm having a problem with the Cyl. So I don't know if the Cyl is minus, but let's see. And I will pass this to the other side. something like that. I'm not so sure because this solution is not on the book. I'm just trying to solve by myself. I don't know, and if you write something like that, um, um, so we can take the arctangent and extract alpha, A10 to um, if this signal is minus and we rearrange this equation um, in a way that sine of A cosine of alpha minus sine of A cosine of alpha, so this way we got 0. So maybe we can rewrite this and we got 0. Right here we can now rearrange the equation. Let's see right here also. If we change the signal, right here we got 0. And right here is the same if we rearrange the equation, and also of course changing the signal for -1, so we got 0 right here. Let's try again. So minus sine of alpha, sine of the A plus, right here we also will have to change. Let me already change the signs. Cosine of alpha, cosine of the A minus, or sine of alpha, sine of the A minus cosine of alpha, cosine of the A, 0, 0, 0, right here 0. I don't know, let's see. Sine of alpha, sine of the A minus cosine of alpha, cosine of the A. and 0 and 0. And 0, 0, 1, 0. And right here, R sine of alpha, sine of A minus R cosine of alpha, cosine of A, 0, L, and 1. Okay. And let's try to write now this. Or sine of alpha, sine of A, which is equal R cosine of, for cosine of A, R sine of alpha divided by R cosine of alpha, which is equal GAR. But we have to solve for phi A, not for alpha. Let me see right here how we have done. Okay, this way. Let me copy and compare. Because of this nx. But right now we are on the cylindrical one, not on the Cartesian one. Okay, so this is the tangent. to know the tangent for extract the phi A, because the relation between tangent, sine, and cosine is this one. Okay. Now let's try to find another clue to solve for. Let's see now is for phi O. How can we solve for phi O? We solve for phi O this way. Just to use as reference. So what other equation we can write? Well, we don't have too many options right here. Let's see. We can use this equivalence between this first element and we can say that is equal to cosine of phi O cannot forget this comma right here. And again, for extract the angle, we got a element equivalent on the Cartesian. Talking about the Cartesian, which is equivalent to sine, and this whole term is equivalent to cosine. And right here, the problem is that I'm writing with cosine and sine. Okay, so I just realized that we need to have a pair. So this pair is composed of one of them is a cosine and the other is the sine. Right here, let me just correct this cosine of n, cosine of n. Okay, so just like we are doing for the Cartesian one, let me show to you. So for each angle we have a pair. So of course on the Cartesian we got these coordinates, but it's like right here a sine and a cosine, and again a sine and a cosine component. So is a pair composed by cosine and sine. Right here we end up with the same resolution. a sine and cosine pair, and I need to write for phi o. Let me see. And the problem is that I'm getting phi o equals 0. Sine of phi o equals 0. And I don't know. I will just write this. So sine of phi o equals 0. Okay, I'm not so sure, but this is a solution. And if we take from here the tangent, knowing this relation, we'll end up with this solution for the phi o angle. So it's something like, what if this was 0? Right here, we'll have a problem. Okay. And um okay. And now the solution for phi n. Just to use as reference, let's see. Again, is a pair. A pair with cosine and sine components. For phi n, let's find right here phi n. Right here, phi n and cosine of phi n. Let me see if I do it right here. I was using cosine of phi o. Right, cosine of phi o. So we can even do it this way. For cosine of phi o, for phi o, right here also, which corresponds to 0. For phi o, and for phi a, and now for phi n. So for phi n, we got this one. Which is equal cosine of phi n. Alright. And for sine of phi n, 0 also. Minus sine of phi n, which is equal to 0. And again, tangent so phi n is equal a tan 2. The first component is 0, and here is where lives the problem. Okay, I'm not happy with these results. We will try to use these solutions on the next video, solving again this example 2.22 of the division. Actually, we can try to solve at least for phi a, But the problem is that for phi A, we already have solved, and we find this minus 6 degrees on this example 2.22 of the tradition. And let me see. We have used with these components inverted. Right here I'm doing cosine and sine, and right here we got sine and cosine. But let's see. Anyways, I'm not sure about this resolution, about the solution, because it's not on the book, but we will try to use them. And this is the second way to solve this problem, this example, and we'll try with the most convenient way and try to find the correct results. And after we got satisfied with what we get from these problems, we can jump right to Euler's angles. But before, we are still cracking these problems. This is it has become a problem in which we have to try to solve, and we need to get out of here with a solution, with a satisfactory solution. And for now it's all. Sorry if I have said something wrong, and that's it. Thank you.